This is part 2, where I'm going to answer the question, what torque and power can a brushless motor provide? I'm going to use a special test rig that I've made, so let's go into my garage and have a look at it. Hi and welcome to my garage. Here's my test rig. It's very simple. This is the key component of it. It's a 2 kilogram piece of steel that's bolted straight onto my motor shaft. The test rig works by harnessing something called inertia. Inertia, it's a property of any item with a mass which quantifies its resistance to acceleration. So its resistance to either moving from a standstill in any direction, or if it's already moving faster or slower. Regular movement is quite simple and it's governed by the equation force equals mass times acceleration. But rotation's different. The equation is torque or turning force applied equals rotational inertia times angular acceleration. So rotational inertia is something that this flywheel has around the rotation axis. And the amount of rotational inertia it's got, it depends on how far away that mass is from its centre of it. So if I had another flywheel with the same mass but bigger diameter, it would have more rotational inertia because the mass is further away from the rotational axis. So going back to the equation from earlier, because I designed this flywheel, I know what its rotational inertia is because I can measure it from the CAD package or actually calculate it. So if I apply a torque or a turning force to it with my motor, it'll accelerate. And if I can measure the speed that it's turning at against time, that allows me to calculate that angular acceleration part of the equation. Then the only unknown left is the torque. So I can calculate it from that data. So to give me the motor speed data, I'm going to actually use my electronic speed controller there. It outputs it directly. I can log it on my laptop. So I don't need any additional sensors at all. Keeps things nice and simple, which is the way I like things to be. I've added a bit of niceties to my test rig here. I've got a safety strap there in case this main beam comes off. I've got a steel box around the flywheel just in case the bearings go on the motor or the motor shaft breaks. I think that should contain it, but if it doesn't contain it, it should at least slow the flywheel down before it does too much damage. Hopefully it doesn't though. So next let's look at the test rig in action. Firstly, we're going to look at the torque curve and how it varies with current and voltage. I'm focusing on torque because that's what we actually need to drive our RC vehicle forwards. We're going to introduce the torque curve and have a look at how changing the phase current affects it. So what we're looking at here is the raw data that I've measured from my motor. It's a plot of motor speed in RPM against time. And what we can see is that when we start applying the constant phase current about here, the motor accelerates with a pretty much constant rate shown by this straight line portion of the curve, and then it tails off. And that's because the acceleration of the motor is related to the gradient of this graph. So with that calculated gradient and using the formula that I mentioned earlier, I can turn that into a torque curve for the motor, and that's what I've got here. So we can see that the motor develops a pretty much constant torque from about 1000 RPM up to 5000 RPM, and if we could go right back to 0 RPM, that constant torque would carry on back to there as well, and that is what's called the constant torque region of the motor. And after about 5200 RPM, the torque goes down to 0 and eventually the motor goes at a constant speed. So why is that? Well, let's go back to our graph from part 1 of the series. So this shows that between the braking voltage or the back EMF curve of the motor and the battery voltage, we've got an achievable voltage difference that we can use to drive current through the motor. The interesting thing is, we don't actually need all of that achievable voltage difference to drive a constant 45 amp peak phase current through the motor. So we need this green curve here, which is just parallel to the back EMF curve. So we want a constant voltage difference. As we go up this curve, eventually we reach a point where we meet the battery voltage, so we can no longer apply that constant voltage difference anymore. That's called the base speed of the motor for that current. And as we go above that, the voltage difference reduces, so the current reduces and the torque reduces until we reach the steady state no load RPM. So this is what we're seeing on our torque curve from earlier. So after it's got to that base speed that I mentioned there, the torque reduces and eventually we reach a steady state RPM and the motor doesn't accelerate anymore. But what happens if we work at a higher peak phase current? What's going to happen then? Well, that's what I did. I did the same test but with 60 amps applied instead of 45 amps. And you can see it's just shifted the curve upwards. And that makes sense because, as I mentioned in part one, torque is proportional to current. So if we increase current, we should also increase torque. And luckily that's showing that and proving it. But interestingly, the base speed seems to have come earlier in the RPM range. Why is that then? So again, if we go back to our little diagram here, this is the same setup that we had a minute ago with the green curve. And what we've done, to get our higher phase current, we've increased our voltage difference. So we've shifted that curve up a little bit more. And you can see that what happens is it hits the battery voltage at an earlier RPM than it did before. So that's why we've seen the base speed get reduced. And we can just see this again if we add a 75 amp curve to our plot, which I managed to measure. We get a pretty much similar jump in the torque measured. And I did get a measurement for 90 amps, but not enough to plot a full curve. There was some strange issue where the motor started making this horrible screeching noise. You've got to see this. So this is 3 cell, 90 amps. It's cut. Now let's have a look at the relationship between torque and current. So if we plot our peak torque values against current, we can see they're close to a proportional straight line relationship. So this is a straight line that I've drawn through the first 2 points at least, but then when you get to the 75 amp point, and even more so the 90 amp point, there's quite a difference from that straight line. We're going up the same in current, but we're not going up the same amount of torque. But why is that then? And it's due to a phenomenon called saturation. This is where the iron stator around which the cores are wrapped, it's got a limit in the density of the magnetic field within it that it can sustain. So as we get towards that point, the torque increase isn't going to be as much as what it should be theoretically, for the current we've given. And it's also worth reminding ourselves that the motor will also have a current limit, usually given by the motor manufacturers. So what we've seen here is that you can't just keep adding more current to get more torque, unfortunately. It would be brilliant if you could, but you can't. What the current limit is, it's related to the thickness of the wire used to make the motor cores and how well it can lose heat. And it can vary a lot, even between motors of the same design but with different kV values. And that is important. We need to keep that in mind because we can see that if our current limit was only 45 amps, it's going to severely limit our torque that we can get from the motor. Say it went from 45 amps to 90 amps, we can nearly double the torque. Now we're going to look at how the input voltage affects the torque curve. And we're going to start by plotting our simple 3-cell test at the steady 75 amps from earlier. So we've got that on our graph there. But now we're going to add a 6-cell test, so double the input voltage from the battery. And the first thing to note is that the torque stays pretty much the same. And that makes sense because we haven't changed the current. But what's changed is that the no load speed has pretty much doubled. So it's gone from about 6,500 RPM to 13,000 RPM. and the base speed is also higher, but it's more than doubled. It's gone from 4,000 RPM to 10,500 RPM. Why is that? Let's go and have a look at our little graph again that hopefully you're getting familiar with by now. So we've got the back EMF going up there again, the 3S battery voltage there, and this shows our no load speed and the base speed for that 3-cell configuration. So when we double our battery voltage, we're able to carry on providing voltage to our motor, keeping that current flowing to a much higher point. So you can see that our no load speed has pretty much doubled there. But what we can also see is that there's a constant offset between our no load speed and the base speed, and that's the same for the 3-cell test and the 6-cell test. And that's because that is a constant offset set by the amount of current that we're flowing through the motor. So if we change the current, then we would see this changing, but for the constant current, we're seeing the same sort of constant reduction from that no load speed to the base speed, regardless of what voltage we're applying. So we can check that again when we add a 9-cell run, and so we can see again the base speed showing the same increase as it did from 3-cell to 6-cell, but there's still that offset from the no load speed. An interesting thing to note here though is that the torque is no longer constant, and I'm not entirely sure why this is. It could be due to voltage sag from the input voltage of the battery, which was significant during the test, or due to eddy current losses. These are a source of inefficiency in electric motors that result in the heating of the stator, and it's proportional to the square of the motor speed, which makes sense because this loss seems to be getting greater as the motor speed gets higher. And you might notice that I'm getting the RPM up to 20,000 RPM in this test, or even over that. You've got to see and hear this. Well, that was my most successful run so far. That was some serious RPM. Blimey. So now, as promised, we're going to look at the mechanical power that my motor's generating. These plots are made by multiplying speed by torque, and they show that for each curve, be it the 3-cell, the 6-cell or the 9-cell, the peak power corresponds to the base speed of the motor. That shows that we can get the best performance for a certain phase current at the base speed. What else can we learn from this? Well, let's compare it with the electrical power consumption that we're putting into the motor. I think these are important to understand. So here's the formula I just used to calculate the mechanical power, and it's power in watts equals torque times angular velocity. But we can calculate the power in two ways. And power, just to recap, power is actually the rate of energy production or usage, and it can come from either mechanical ways or electrical ways. So the electrical power, that can be calculated by the input voltage that we're applying with our battery, and also the current from the battery. So the volts times the amps basically equals the watts. And then there's also a relationship between these two, which is the efficiency. And efficiency is basically a measure of how good the motor and the speed controller are at converting the electrical power we're putting in into the mechanical power that we're getting out. It'll always be less than 1. Let's work out the electrical power, but first we'll remind ourselves what's going into the motor from the speed controller. So this is what we're seeing from the electronic speed controller unit into the motor phase itself, and this is the constant 75 amps that I was saying that we're applying earlier, which then gives us our almost constant torque through that region up to the base speed. But then what are we having to put into the speed controller from the battery to provide this constant phase current across the 3 motor phases? And it's, yeah, spoiler alert, it's different. And this is what it is. So this is our plot of our input current from the battery versus RPM. And you can see that it varies quite linearly as the motor speed increases, but from quite a low value. So it starts at only about 10 amps and goes up to about 55 amps, despite the fact that our phase current is constant and much higher at 75 amps. And this is due to the fact that the effective voltage being applied by the speed controller increases, the RPM increases because of that back EMF effect, and the fact we need to keep that constant voltage difference between the back EMF and the what we're applying to drive the same current through the phases. I'll be covering more on that and how that's actually achieved by the speed controller in a later video. The voltage we're putting in from the battery, that is almost constant. So for the 9 cell we're putting in, we're starting at about 36 volts, but it sags down to as little as about 32. But it's almost constant really. Anyway, to get the electrical power going in, we multiply these 2 curves together. Unsurprisingly, the curve shape is almost identical to that of the input current, because the voltage was almost constant. All we see the difference from the current curve to the power curve is that it tails off slightly due to that sag in the voltage as we got to the higher power area. So if we put the mechanical power curve on that we'd already worked out, we can see that it follows a similar shape to the electrical power in curve, but it's always less, which makes sense. That's what I said before. The efficiency, which I've also calculated and added here, it's always less than 1, so it's 90% between about halfway through the rev range up to the peak revs, and that looks very nice. But just remember though, we're actually, even at 90% efficiency, we're throwing away 10% of our power into losses. And what are those losses? So basically what we're doing with that 200 watts of energy at the peak power of the motor, it's going into heating up the motor and the speed controller. To summarise, what we've seen then is that torque is proportional to phase current, although as the current gets higher, the torque doesn't go up quite as much as you think it will because of saturation losses. With that limitation and also the current limit of the motor itself, it shows that you can't just keep adding current to get more torque out of your motor, unfortunately. We've seen that adding voltage increases the base speed of the motor, but we've seen that as the RPM gets higher, eddy current losses start coming in, which give a significant reduction in torque. So we've found that you can't just keep adding more cells and expect the torque to remain constant as the RPM goes up. We've seen that the peak power for a certain phase current comes at the base speed, so maybe we should be aiming to operate at or above the base speed. So more on that in some upcoming episodes. And we've seen that the motor has an efficiency of less than 100%. The mechanical power you get out is always less than the electrical power from the battery due to losses. Believe it or not, it's possible to calculate the torque and power curve of a motor that you don't even own. Then, with an estimate of the powertrain efficiency, we can calculate the input battery current and voltage that we need to drive that motor. Altogether, that's going to enable us to make better powertrain choices for our RC vehicles with less trial and error. And personally, I almost couldn't believe this would be possible when I found this out, because it's going to help me so much with my speed car engineering going forwards. I'm really excited to share this with you in the upcoming parts of this series. So please like and subscribe so you don't miss them.